Last time our discussion was application of the VBT and various complexes I discussed. And it's the interesting thing that all you have answered correctly. If only if I give the information whether that ligand is strong or weak, you could able to find the hybridization. From that the structure will be the clear. And again from electronic configuration in the complex, magnetism will be clear to you. No doubt qualitative magnetism it is giving, but at least we'll come to know how many unpaired electrons are available. I want to know how many of you know the formula to calculate magnetic momentum. Magnetic momentum is equal to
Square root n plus
right square root of
n
complete it
n plus 2.
n into n plus 2 Bohr magneton. Brilliant. What is n? N is
Number of unpaired electrons.
right, number of unpaired electrons, that number n. If you know the number from the electronic configuration, you can find the magnetic moment. It was a simple aspect for what the valence bond theory to find the magnetic moment. So perfectly we may not get, but rough idea at least about the magnetic moment we could get. That's a benefit, that's an advantage, that's an application of valence bond theory. So in short, if I have to say what's the use of the valence bond theory, then first use to explain the structure or geometry of the complex, and second use to predict or to get the idea about the magnetic property of the complex, about the coordination compound we are seeing. Previously when I talk about the spin only formula, it was regarding transition series metal ions and in general compounds. Here we are discussing about the coordination compounds, and to explain the properties of coordination compound, one of the theory that we studied, that's a valence bond theory. Actually before that Werner's theory is there. In 11th 12th also you have studied, and in videos, short videos which you have prepared, a rough introduction about the Werner's theory also was provided to you. Therefore I had not discussed now the Werner's theory. After Werner's theory, now the theory which you are studying is a valence bond theory, and after that you will study, that's a part of the next year syllabus, crystal field theory. Crystal field theory also is with the limitations. Then you will study the molecular orbital theory. Likewise, stepwise progress is there. And students, coordination chemistry is one of the important aspect in the chemistry, one of the important topic in the chemistry for research point of view as well as competitive exams point of view. Whatever I discussed till now about the various applications, if you have any doubt, you are free to ask. Otherwise, I am asking you the question as a revision. Okay, fine. If you don't have the question, then I ask you the question. FeH2O6 plus 2. I want answer for hybridization, and I want answer for number of unpaired electrons n, and I want answer for magnetism. These three questions you have to answer. Let me know who can answer. What will be the hybridization? Data I am providing that water here is a weak field ligand. Weak ligand.
sp3d2 hybridization.
Good. It's outer orbital complex sp3d2. Brilliant. Good answer. Correct answer. Number of unpaired electrons. For that, which is a central metal ion, that you have to find out. That central metal ion is Fe plus 2. Hint I am giving. And atomic number of iron is 26. Hint I had given to you.
3d6.
Okay, 3d6. I want number of unpaired electrons.
4.
Good.
4.
Whoever have given 4 as answer, correct. Means they are applying magnetism.
Paramagnetic.
Good. So if you know whether that ligand is weak or strong, you can guess outer orbital or inner orbital. From that hybridization, from that of course geometry. Hybridization sp3d2 octahedral complex. So octahedral will be with the geometry. That idea you will get. Shall I ask one more question?
Yes, sir.
Yes, sir.
Yes. Now I want to ask about one complex, very important complex. In laboratory also that complex is there. Potassium ferrocyanide. Which central metal ion is there, that you have to find out. And as I asked last time, here also I want the answer for type of hybridization, for number of unpaired electrons, and for its magnetism. From hybridization structure, that's the application of VBT. Cyanide. Cyanide is which kind of ligand? Last time I discussed that. Let me know who knows that.
Strong.
Cyanide is brilliant, strong field. So from that hybridization will be 6 is the coordination number. Then two possibilities are there. sp3d2. Last time we discussed outer orbital complex, and now possible d2sp3. Yes. Which hybridization is possible?
d2sp3.
Yes, good. d2sp3 is the inner orbital or outer orbital complex. This complex is the inner orbital or outer orbital.
Inner.
Right, inner orbital. Just this word terminals are important. Later on, we will know something about that. Number of unpaired electrons. Again, here metal ion is ferrous, Fe plus 2. Atomic number is 26. Find number of electrons and inner orbital. So against Hund's law of maximum multiplicity, pairing will be there. See if two inner orbitals are made available, what will be the electronic configuration? Yes, I want number of unpaired electrons. Do you think it is difficult? Somebody was saying, Saurabh, I think, was answering. 4. Saurabh is saying 4. Saurabh, it is an inner orbital complex. Inner d orbitals are to make available considering that answer for the question. I give further 1 minute. Within 1 minute, I want answer. Pratham is saying 2. 2 unpaired electrons. Okay. So one answer. Chirag saying 2 unpaired electrons. Okay. Good. Okay. Shilpa saying 2 unpaired electrons. Okay, okay. Farin saying, okay, majority of you are saying 2 unpaired electrons. Let us validate whether Saurabh is correct or majority is correct or nobody is correct. That we will find out now. Shall we find out now? At least answer.
Yes, sir.
Yes, sir.
Okay, see. Central metal ion is Fe plus 2. About that, any problem?
No, sir.
Yes, sir.
Atomic number of iron is 26. So, if I have to talk about mere iron, only iron, then its electronic configuration will be outer electronic configuration 3d6. Why 6? Last digit 6 and 4s2 and 4p0. It is electronic configuration of Fe plus Fe. But here Fe plus 2 is there. What will be its electronic configuration? 3d6 4s0 4p0. How can I write that electronic configuration in terms of the block diagram? See, d orbital I am representing here. Here s orbital and their p orbitals are there. So how many electrons are there? Total 6 electrons. So how? First electron, second electron, third, fourth, fifth, and sixth. Any problem about the electronic configuration?
No.
No.
Good. So there are 4 unpaired electrons in Fe plus 2 in ground state, in free state. But our Fe plus 2 is not free. It is forming complex. And which complex? Octahedral complex. With whom? A giant, great ligands like cyano or cyanide. Strong field ligands, close friends, close relatives. In such cases, what iron has to do, what ferrous has to do, what Fe plus 2 has to do, Fe plus 2 has to make inner rooms available, inner vacant orbitals available. And somebody rightly said D2sp3 is a hybridization. If I want D2sp3 as a hybridization, then here electron should not be there. Here electron should not be there. So only I am with these first 3d orbitals where I can put electrons, and in remaining orbitals electrons from ligands will come. D2sp3 hybridization, one ligand, second ligand, third ligand, fourth, fifth, and sixth. That's what the hybridization, D2sp3 and electrons in those hybrid orbitals. Our point of interest is electronic distribution. Now 6 electrons I have to distribute here. So rule is same, pairing against Hund's rule. So what will happen for those electrons? First 2 electrons will enter in first orbital. Next 2 electrons will enter in second orbital. Next 2 electrons will enter in next orbital. How many electrons are entered now? 6 electrons are entered. Now tell me, how many unpaired electrons are there? Question was unpaired electrons.
0.
0.
0. So here number of unpaired electrons, if I have to represent, then those are what? 0. So what were your answers? Few were saying 4, means one was saying 4, many were saying 2. How were you saying 2? I don't know, but here that answer also is wrong. Correct answer is 0. Is it clear?
Yes, sir. Yes, sir.
Yes,
Then
sir.
what's the magnetic property?
Diamagnetic.
Diamagnetic.
Good. Yes, here is your understanding. If you go to the syllabus, then you will find, see, inner and outer orbital complexes. Examples they have given: Mn plus 2, Ap plus 2, Ap plus 3, Co plus 2, Co plus 3, Ni plus 2, Cu plus 2, Zn plus 2. I did not discuss all, but several among them are discussed. And especially what they want: ligand like aqua means water, ligand like ammonia, amine, NH3, ligand like Cn minus, cyanide, and halide ligands. So F minus ligand or Cl minus ligand, last time I discussed, cyanide ligand I discussed, amine also discussed, and all ligands are discussed. In addition to that, carbonyl also I discussed yesterday. Purpose is let you know to apply valence bond theory. And it's a very good thing. At least 50%, at least I'm saying, insight is there with you about the valence bond theory. Am I right?
Yes, sir.
Yes, sir.
Yeah. So if any such examples come out there, you could able to answer. So today I plan to discuss limitations of valence bond theory. Where valence bond theory is wrong. It seems to be the very simple. It seems to be the very interesting. People have were fond of with that valence bond theory. Almost about Miss 1917 it came out up to 1937, almost 20 years. Valence bond theory was ruling for understanding of coordination compounds, because due to Alfred Werner, doors of coordination compounds were open. Coordination chemistry newly was started, and to explain that, Linus Pauling theory, we can say, as a valence bond theory came up, and for 20 years almost it was ruling. But later on people come to know the theory which we are considering as a correct theory, somewhat correct from their point of view, from their perspective point of view, from their applications. Say the magnetic property application were there, structural explanations were there. Then they found for which this valence bond theory is known. That's a structural finding, structural determination for which this valence bond theory is known to explain the magnetism. Their only problems are there. There also problems are there. For few complexes it is proper, but for many complexes it is not explaining. And still many things are there about the coordination compounds about which we can talk, about which valence bond theory was silent. So what are the limitations of valence bond theory that I am discussing? For that, one interesting example that I give it to you. Color of that complex is blue, royal blue, you can say, dark blue, and that complex is of the metal ion copper plus 2. Complex is of the metal ion copper plus 2. Complex is blue. Ligand is, anybody knows what is that ligand? Famous complex it is. Means while studying in 12th standard, if anybody knows, therefore I am asking, what is that ligand? Let me see who can complete. What is the ligand? At least complete. Which ligand you know from this formula, or complete that formula? Something is here.
NH3.
Right,
Ammonia.
amine, ammonia is a ligand, and complex has coordination number 4. Coordination number 4. So what is its formula? Its formula is CuNH3 4, and charge on that complex is plus 2. Are you following?
Yes, sir.
Yes, copper amine complex about which I am talking now. So blue colored copper amine complex, it was a puzzle in front of many, but because of Alfred Werner, somewhere people got the insight that ligands are there which surround the metal ion. Now when we apply valence bond theory, then what happens? See, as per valence bond theory, we will talk about first point, that's a central metal ion. Will you answer which central metal ion is there? Ammonia carries no charge. Neutral ligand it is. Which central metal ion?
Copper plus 2.
Right. Cu plus 2. Second point is our electronic configuration. So you can write the electronic configuration for that Cu plus 2 directly. What electronic configuration? 3D. Yes.
9.
3D9, 4H0, 4P0. For the sake of brevity, I represent it in terms of block. Afterwards, here the 4S and then 4P. 9 electrons are there. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth. Means one unpaired electron is there in free Cu plus 2 ion. Here vacant orbital, vacant orbital. Coordination number is 4. If coordination number is 4, so at this moment, as per your knowledge, which types of hybridations are possible? For coordination number 4, which types of hybridations are possible? One hybridation is, yes,
sp3.
right, one hybridation is sp3, and other possible hybridation is,
dsp2.
DSP2.
right, dsp2. Here ammonia is a strong ligand. Here, in this case, ammonia versus strong. So if it has to make available one of the d orbital as is needed here, that's one of the d orbital, if it make available, there's no chance because 9 electrons are there. Here only 1 electron left, no? So this orbital cannot be made available by usual course, by usual means. Are you understanding what I'm saying? Yes, are you understanding?
No,
See,
sir.
dsp2 is hybridization.
Repeat, sir.
Repeat.
I repeat, yeah. Coordination number 4, two possibilities are there. One is sp3 and other is dsp2. Ammonia is a strong ligand here. So if ligand is strong, then as far as possible, close relative, then what you will do? You will make available inner rooms. vacant rooms. So whatever the copper is with these 5 rooms in the d orbital, and already copper is with itself own electrons, 9 electrons. So copper is with no more space available. Here unpaired electron is there, and more than 2 electrons cannot stand in that one room in one orbital. So even if copper wants to give room for the ammonia, for room for the ligand, copper cannot give. Copper cannot do that provision. Why? Because it itself is with that capacity, it itself is that number of electrons. So despite of the want of the copper, copper can't make these inner electrons available. Are you following?
Yes, sir.
Yes, sir.
Yes,
Yes.
sir.
Okay. So only option left. What should be the hybridization? What should be the hybridization? Which hybridization should be there?
TSP2.
No, d orbitals can't make available, no?
SP3.
SP3.
sp3 sp3 will be the type of the hybridization. Here see, sp3 will be the type of the hybridization. If sp3 is the type of the hybridization, this complex should be tetrahedral. It is as per the our knowledge of the valence bond theory, as per the application of valence bond theory, as per the basis or postulate of valence bond theory, tetrahedral should be the geometry. But what is the reality? In reality, this complex was found to be square planar. So problem come in front of Linus Pauling. How to describe that? So for the description, what he did, he said that complex undergoes rearrangement. Metal ion undergoes that rearrangement. I repeat, practically this complex was found to be square planar, which was very difficult for valence bond theory to describe the square planar geometry as per usual concept or as per its understanding, as per its basis. Then Linus Pauling said, whichever electron is here now in this orbital, electron is there, this electron excites to higher orbital. Means I represent an electron here. This electron excites to higher orbital in order to make available this one of the d orbital, and already s orbital is available, already further 2 orbitals are available, so that it will be easy or convenient for that Cu plus 2 to undergo this hybridization. What is this hybridization? DsP2 hybridization. And if DsP2 is a hybridization, then what will the geometry? Square planar will be the geometry. So my theory is correct. Means it was his view, Linus Pauling's view. So what Linus Pauling did, he excited the electron present in the d orbital, excited that outermost unpaired electron present in the d orbital to higher p orbital, and due to which DsP2 hybridization was made possible, and in those hybrid orbitals the electrons from the ligands will be there. It's the electron from one ligand, electron from second, from third, and from fourth. Are you understanding at least 20%?
Yes, sir.
Yes, sir.
So
Yes,
what
sir.
happened? Shortly, I'm repeating that point. Those who were not attentive, pay attention now. Complex I am discussing is copper ammonia complex. Central metal ion is copper plus 2. Outermost electronic configuration is 3d9 4s0 4p0. As per electronic configuration, one unpaired electron is there in that free metal ion. And if coordination number is 4, 2 possibilities are there. One possibility is tetrahedral and other possibility is square planar. As per our previous logic, whatever may be the strength of the ligand, that's the ammonia ligand, since there is no space available inside, sp3 should be the hybridization, tetrahedral should be the geometry. It's a simple application of valence bond theory. And Linus Pauling found valence bond theory is failing there. So in order not to fail, what he did, he excited the electron present in the last d orbital. Here one electron was there. That electron he excited in one of the p orbital in order to make available which orbitals? This d orbital, s orbital, and p orbital, dsp2 hybridization, in order to explain its geometry, square planar. This is the application of valence bond theory, Linus Pauling. But where is the problem? We are talking about limitation. Limitation is unwanted excitation of the electron. Unnecessary. Such excitation will not occur. Electron is not likewise whenever we want, we will plus otherwhere. That explanation is scientifically not acceptable. In such cases, if it happens over there, it is ionization. Cu plus 3 would have been possible there. So practically, excitation of electron is not going to occur. Electron is not moving out. If it is not, then how can that VBT or Linus Pauling theory describe the geometry? Here is a problem. Theory seems to be simple, And whenever it necessary, unnecessary electron excitation that Linus Pauling has recommended, it was not scientifically acceptable, and that's a great limitation of valence bond theory. That's the first limitation of valence bond theory I discussed with you. Is that limitation clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Now, second limitation that I am talking about. Complexes are colored. Many complexes are there. They are with color. But how can color be described? Color be explained? Nowhere valence bond theory attributed the explanation for the color. Are you understanding what I am saying? Yes, students, are you understanding what I am saying? Yeah, shortly only I said colors were not explained by VBT. What's the general idea about the color? I told you while discussing the transition series Metline, color one sees is due to. Color one sees is due to. Complete that.
Absorb.
Right.
Absorption or reflection.
Absorption. Absorption. Absorption of what? Electromagnetic radiation means light or the photon. What happens because of absorption? Electronic transition or excitation occurs. Electron moves from one level to other level. Level should be there, no? Then excitation will be possible. Here, as per valence bond theory, all d orbitals are there of one energy level. There is no splitting. There is no energy gap. There are no separate levels. If levels are not there, excitation is not possible. If excitation or transition is not there, absorption will not be there. If absorption is not there, color should not be there. But colors, what one see is due to the absorption. And about absorption, about splitting, about different energy levels, valence bond theory has not given any description. So valence bond theory could not explain the colors of the complex. It is a limitation people found after 20 years of valence bond theory, after 20 years of application, people realized that it is a limitation. Means by 1937, people realized somewhere we need to shift to the other theory. So second limitation of valence bond theory is color. What was the first limitation? Could not describe the geometry of copper-amine complex CuNH342+, which is practically square planar. But explanation for square planar geometry was not acceptable. First limitation. Second is what? The color. Is this second limitation clear?
Yes,
Yes,
sir.
sir.
Yes. Now, third limitation about which I am discussing stabilities. Coordination compounds remain with various stabilities because every compound cannot be of the same stability. Every individual how remains different. Psych stability or mind stability of everybody's remain different. Likewise, complexes also they are with their own stability. Stability constantly more clear next year. But timing remember they are with different stability. Who will be the most stable? Who will be the less stable? What will be the exact stability about which it has not given perfect explanation. Qualitative explanation is given. Means what? It is more stable or it is less stable. That explanation is given. Which complexes are more stable? Inner orbital complexes are more stable, and which are less stable? Outer orbital complexes are less stable. Why inner orbital complexes are more stable? Because close relatives, good bonding. Inner orbitals are made available. Inner orbitals, so strong interaction. Strong interaction means more stability. And outer orbital is not close relative. Outer orbitals will be made available because of they are less stable. Likewise, explanation valence bond theory is given, but we are not happy with that explanation. Suppose if I consider two inner orbital complexes, say Fe(Cn)6 minus 4 inner orbital complex, other copper amine complex, chromium amine complex we consider, or cobalt amine complex we consider CONH3 6 plus 3. Both are inner orbital complex. Among them, who is more stable or less stable? No idea as per VBT. That is a limitation of valence bond theory. Valence bond theory could qualitatively describe stabilities roughly, broadly, inner orbital, outer orbital, more stable, less stable, enough. Those that much only explanation. But perfectly how much stability, quantitatively measurement, how we can measure the mass, how we can measure the volume. In that way, can we measure the stability? Yes, it is possible. But at that time, people were not knowing on the basis of the VBT. That is a limitation of valence bond theory. Are you understanding this limitation?
Yes, sir.
Yes, sir.
Yes, sir.
Shortly, inner orbital complexes are more stable, outer orbital are less stable? Simple, general, broad explanation valence bond theory has given, but particularly, what is that stability? What is the exact stability of the complex? Particularly, comparison between the stability. We can say no, number 2 is less than the number 3. 3 and 2, quantitative measurement is there. We can compare. Likewise, comparison valence bond theory has not done. That is our third limitation. Now, the fourth limitation of the valence bond theory is about liability. Previous point was stability. Now, this point is liability. What is this liability? Liability is related to exchange of the ligands, or simple way, chemical kinetics you have studied, no? It is related to speed of reaction and their substitution reactions we are considering. Maybe nucleophilic, maybe electrophilic. Timing, let us understand only reaction, substitution reaction. Speed of the reaction. Which complex can we say as a labile complex? If its speed is high, speed of the reaction, speed of the substitution is high, such complexes are labile complex, and this lability concept is kinetic theory concept. Stability concept is thermodynamic concept. Kinetics and thermodynamics, two different aspects. In physical chemistry, you are studying them in detail. That application we are doing for inorganic chemistry. Kinetic data for the complexes, lability, inertness, about which this valence bond theory could not give satisfactory explanation. It is the fourth limitation. Are you understanding this limitation?
Yes, sir.
Yes. Shortly, I tell to you.
Yes, sir.
Stability, thermodynamic consideration. Lability, kinetic consideration. Kinetic theory related to speed of the reaction. Here, yes, speed of the reaction when it remains high. Such complexes are labile complex. About liability, VBT has not thought at all. Comparison, separate thing. It is a great limitation of the valence bond theory, or serious limitation. Next limitation, that's the fifth limitation, is the application of valence bond theory. We say no, valence bond theory could describe the magnetic properties of the various complexes. Yes, certainly. It has served to the great extent to describe the magnetic property of the complexes. But what is found for few complexes with change in temperature, this magnetism changes. It is a practical observation, and this practical thing was not explained by VBT, because VBT was considering hybridization, VBT was considering electronic configuration. Absolutely, it is right, but that electronic configuration at this temperature different and other temperature different, likewise no ideas are there, no way is there by which we can change electronic configuration with change in temperature. But it is found few complexes with change in temperature, their magnetism changes, and that property was not explained by valence bond theory. How can magnetism change with change in temperature? And for us also not possible, because it is not there in valence bond theory. But if you study the next theory, you will understand the importance of the next theory, importance of the change in the magnetism with change in the temperature. So what are the real observations were there? If theory could not explain, then that's a limitation of that theory. So it is a fifth limitation of valence bond theory. What is that fifth limitation? It is found that with change in temperature, magnetism changes for few complexes. It is impossible for valence bond theory to explain. That's a limitation. Is it clear?
Yes. Yes, sir.
Yes.
Yes. Now, brilliant students, let us revise now and we will stop our today's discussion. What was the first limitation? Yes.
Geometry.
Geometry of which complex?
Electron.
Copper ammonia complex, CuNH3 4 plus 2, which is practically square planar. But to describe that square planar, Linus Pauling was brilliant. He came to know it is square planar. To describe it square planar, he changed the path. Unnecessary excitation of electron he suggested. It was a limitation. Second limitation,
Color.
colors of the complexes is a reality which was not explained by valence bond theory. Third limitation,
Stability.
complexes are stable or less stable. Partly explanation is there. That's a qualitative explanation. But quantitatively, what extent stability? Relatively, comparison between two inner orbital and outer orbital. It was not possible for valence bond theory. Brilliant. Fourth,
Lability.
lability. Rate of the reaction, speed of the reaction. More speed, high speed, labile is a complex. So that is also an interesting point to study, about which valence bond theory with no answer. And last limitation,
Magnetic.
Magnetic.
magnetic property to great extent valence bond theory explained, but change in magnetic property with change in temperature is not explained. It was not possible by Weisbond theory. Are these 5 limitations clear?
Yes, sir.
Therefore, students, it is a need to study the new theory, and that you are studying in next year syllabus. But afterwards, one interesting point is there: applications of coordination compounds. In order to arouse the interest, in order to know what are the applications in our group, WhatsApp group, I posted one slide, one image. Here, brief applications are mentioned there. Truly, coordination compounds are applicable. Applicable. See, shortly I tell to you, in detail we will discuss. It's an interesting point. And you also be with what the question. Medicinal field, poisoning, copper poisoning, lead poisoning, if is to remove, then this chelate therapy. Chelate therapy means complex therapy. Complex formation therapy is what the use. And important point, what are the blood that we are with? Their important group is there, and that group is called as, yes, in blood what remains?
Hemoglobin.
Yes. Heme group or hemoglobin. So that hemoglobin is a coordination compound. Coordination compound. And because of that, functioning of blood is there. Blood can take oxygen, blood can release oxygen. An important thing, the life is there because of what? On earth, life is there because of which phenomenon?
Photosynthesis.
Right, photosynthesis. And photosynthesis due to which pigment or which chemical?
Chlorophyll.
Right, chlorophyll. This chlorophyll is a coordination compound. Because of its coordination compound, it can absorb one particular photon, and because of that photon, carbon dioxide, moisture, food can be generated. So, see, origin of the life, you can say coordination chemistry. Such important chemistry it is. Its applications are mentioned in detail. We will discuss the application in the next lecture. Part of the time we can use for the next lecture. Is it clear the purpose that I shared that? That's a slide. Yeah.
Yes, sir.
Next time be with that. So you can ask question, we can have discussion. One first application, second application. Just you will answer, I will give the description for those applications. Yes, students. If any doubt is there for today's discussion, if you want to know anything, then let me know. I'll describe that. Okay, no question. Okay, fine. So complete assignments. Assignments I had not allotted. I will allot very soon, but go on completing assignments. Assignments what? Preparing notes for the lectures. Saurabh was regularly taking follow-up, was asking. Prathamesh also do take the follow-up. Many from your class are do take follow-up videos, updating. But it was my mistake, or you can say I apologize for that. That delay is there in last. But today's lecture I will post. Today only I will post that today's lecture, video lecture, provided that recording has took place for the properly. But what happens, I'll inform to you. But be studious, study well, and learn the chemistry more and more. While learning, if doubts are there, problems are there, as a teacher, it's my first responsibility to answer your question. So, students, shall we stop now?
Sir.
Yes, sir.
Yes.
Yes, sir.
So, I declare here today's session is over. Quit now.